and welcome. In this video, I'll be covering the second half of section 7.1, which is more over the sum and difference identities or formulas that we'll have involving trigonometric functions. So again, we've already kind of talked about some of the Pythagorean and basic identities such as the reciprocal or quotient and that sort of thing. This one again is just more focused on just applying the sum and difference. So hopefully if you've watched the first part, you have a decent understanding of where this is about to go. So regarding the sum and difference identities that we'll be dealing with or utilizing, you can see them on the screen currently, or again, they'd be on the formula sheet or in the notes if you want to have access to them while we're working through these. It might make the process speed up a little bit for you. And also having a unit circle, or at least being familiar with the angles and their ratios from the unit circle is also something that could be beneficial. So the main ones that we're going to be dealing with again is the sum and difference. So as you can see, we just have the three main functions of sine, cosine, and tangent that we're going to have formulas for. If I needed to evaluate a secant, a cosecant, or a cotangent, all I would do is approach it as if it were one of these three, and then whatever my final result is, I would then find its reciprocal and simplify. So again, there isn't really any special formulas for the reciprocal ones, sine, cosine, or sorry, cosecant, secant, and cotangent. After all, we just need to figure out what these would be, and then we would just flip the result. Now when it comes to when would I use this, on occasion it might just be if I knew a couple of triangles that one had an angle A in it and then another one had an angle B in it. I could use the ratios that I know from that right triangle potentially to then replace the sine or the cosine or the tangent, depending on which ratio I need, with its value from the triangle, and then simplify. A lot of these problems, though, are going to be ones that utilize maybe an angle we don't recognize on the unit circle or that doesn't exist, at least not with our shortcuts that we've created. But we can then maybe break it down utilizing angles that are on the unit circle. So as an example here near the bottom of the screen, you can kind of see like 75 degrees as an example. If I wanted to use some of the angles that are on the unit circle, what I could do is think of that as like 30 degrees plus 45 degrees, and that technically would have the same value as 75 degrees, but now it would be like an A and a B that I could then maybe utilize inside my formula. So notice inside each of these parentheses, it's either A plus B, or on the right side we have A minus B's, right? All of those basically are just, I want to take one angle, potentially split it into two angles that's using adding or subtracting in some way, shape, or form, and just identify what the A and B would be. So our options for 75 degrees would be kind of limited, but if I went to subtraction, technically there's quite a few that I could attempt to subtract. One example or another example could be like 135. If I subtracted 60 degrees from it, that technically would give me 75 degrees as well. And so if I wanted to utilize those angles for whatever reason instead of the 30 degree and 45 degree that I could break it down into, that technically would also be an option. And I could keep going and going and going, but ultimately it's just, if you can ideally stay in the first quadrant, that would mean you don't have to worry about as many negative signs. So if you can use angles in the first quadrant, cool, to break it down, but don't necessarily always have that ability. So it just comes down to, as long as we can get two angles that are on the unit circle to add or subtract to equal the angle I'm starting with that maybe is not on the unit circle, in this example 75 degrees, then we should be able to follow these identities and still figure out what its either sine, cosine, or tangent ratio happens to be. Now if I had an angle in radians, what we would kind of do is almost reverse what we would normally do with two fractions being added together. I'd actually make it turn into two fractions that keep the common denominator. So in this case 12 for 13 pi twelfths, if that was the example I wanted to break down. And then I'd try and choose some numbers that I know will reduce with the 12s, because after all there are no pi twelfths angles that are on the unit circle. So here I just, as an example, chose 10 plus 3 because that's relatively easy to make the 13. Notice each numerator still has the pi, that way they would combine and turn into 13 total pi. And the parts of 12 on the bottom just stays the denominator for the time being. Once I choose a couple of numbers that I know will reduce with the 12, then I go ahead and try and reduce the fraction. So like 10 twelfths would reduce to 5/6, and 5 pi 6, that one happens to be on the unit circle, as we hopefully know. And then 3 pi twelfths, well 3 twelfths reduces to 1/4, so pi fourths, that one also happens to be on the unit circle. So notice again, I now have an A and a B I could use in any of the I guess, above 6 formulas that we have in the event that I needed to figure out what either a sine or a cosine or a tangent would be. I guess it's technically only 3 since this is addition. I didn't do any subtraction. But there is, again, multiple options I could do with 13 pi twelfths. I could technically make that 15 pi twelfths. And then let's take away 2 pi twelfths. Again, intentionally choosing two numbers that I know have something in common with the 12, so I know that I would be able to reduce. In theory, it should, if I can reduce, especially at least with these examples of 12, it should be able to reduce to either a 6, a 4, or a 3, which are angles that we have on the unit circle to use. So that would be the general idea as far as our approach. In these problems, if I had an angle that was specific, such as like the 75 degrees or the 13 pi twelfths, I would just want to try and use some angles that I am familiar with from the unit circle and know some ratios of, and then I would go ahead and break it up utilizing that, and then start plugging into the formula, which is where we're about to head next. And before I jump too far in, let's go ahead and just maybe practice a couple more of these like breaking down angles. So I feel like more practice can't hurt. So if I wanted to maybe find a way to rewrite 15 degrees, in fact we're actually going to use these two later, so there is some intent behind this, but 15 degrees, I feel like the most logical we could go with would be trying to choose some angles in the first quadrant. One option could be 45 degrees minus 30 degrees. That would make 15 degrees as a result. Another option we could go with is 60 degrees minus the 45 degrees. And I could keep going around the unit circle and so on and so forth. I could do another one like what, 135 minus 120. That would give me 15 degrees. So I'm giving myself multiple options that I could go with, but in all honesty, I would probably choose either that one or maybe the 60 degrees minus 45 degrees, one of the top two, just because those utilize angles that are in the first quadrant. In the first quadrant, usually, again, because there's no negative signs, should in theory be easier to deal with. Now the 17 pi twelfths example, or this part B, that will be a little bit trickier, but ultimately I would just set it up where I make two fractions that both have a 12 on the bottom and a pi on top. And now it's just kind of a fill in the blank. I need to choose a couple of numbers as coefficients here that will add or subtract to give me the 17 that's there. So in this case, let's see, for 17 I would think maybe 15 and 2 would be probably the first example I could think of, but technically like a 9 and 8 would work. I'm just going to commit to the 15 and 2 and just hope that they both reduce. Again, why 16 and 1? Even though, yes, it would make 17, the 1 over 12 wouldn't reduce, so that wouldn't necessarily give us an angle that we would recognize on the unit circle. Each of these, though, if I go ahead and reduce, what goes into both 15 and 12 is a 3, so if I divide each of those by 3, the top would turn into 5 pi, and the bottom would turn into 4, so 5 pi fourths. Notice that is an angle that we recognize hopefully on the unit circle. And then 2 pi twelfths, well 2 twelfths reduces to 1/6, so that's really the same as pi sixths. And again, that would be another angle I recognize on the unit circle, hopefully. So those would be the two that I would maybe choose. Another option, if we wanted to just see one more example of that, let's say we did the 9 pi twelfths and 8 pi twelfths I mentioned not too long ago. 9 plus 8 is in fact 17. Again, I'm keeping the pi twelfths for both of them, but now I'm hoping I can reduce. So 9 over 12, 3 goes into both of those as well, so that would turn into 3 pi fourths. And then 8 twelfths, 4 goes into both of those numbers. 4 goes into 8 2 times, 4 goes into 12 3 times, so 2 pi thirds. Again, notice they both reduce to angles that are on the unit circle, so I could use those as my A and B, or I could use the 5 pi fourths and 1 pi sixths as my A and B. Just kind of depends on what am I trying to accomplish. Am I trying to do a sine, a cosine, or a tangent? If so, I can use one of the sum formulas that hopefully we either have referenced, written down, or just somewhere in the notes that you can easily access. But the next few examples are just now going to be not only breaking angles down, in fact we'll actually just use these, but we'll actually plug into the formula and kind of see how the formulas actually work. Alright, so our first example here, or continuation of the examples from the previous one, I guess the sixth total example, but second one in this video. Let's go ahead and just kind of break this down. Again, 17 pi twelfths, if I needed to find its cosine. Ideally, if it was an angle on the unit circle, I would just reference the x value. But obviously 17 pi twelfths is not one of the angles. If you looked around, I don't think you'd ever find it. So this is one where I might want to rewrite it using a couple of angles that I do know on the unit circle. So 17 pi twelfths actually was the same as what we just broke down before. So that one, if we recall, the first example I think was 5 pi fourths added with pi sixths was the pair that I had, but again, that was like doing 15 plus 2 and then reducing 15 twelfths reduced to the 5 fourths, and then 2 twelfths reduced to the 1 sixth. That's kind of a weird looking 6, sorry about that. But now I can identify that this would be like the A in the formula and this would be the B in the formula. So since I'm trying to do cosine, and I do have specifically, as we can see here in the middle, I am adding, the formula I would want to do is going to turn into what is the cosine of A times the cosine of B. And then oddly enough, even though it's addition here, the formula will switch to subtraction, and then it's basically the two sine ratios multiplied together as well. So now if I go ahead and do maybe that substitution in place of the A's and B's that we see here, this really is going to turn into what's cosine of 5 pi fourths times what's the cosine of pi sixths, and then minus the result of multiplying the sine of 5 pi fourths with the sine of pi sixths. So at this point, all we're going to do is just reference what the ratios actually are on the unit circle and replace them with their values. So cosine of 5 pi fourths is a value. If I go ahead and maybe sketch a visual of where 5 pi fourths is, it should be the middle one in the third quadrant. So if we think about the middle angles, those are always a rad 2 over 2 paired with another rad 2 over 2. It just happens to be in this quadrant, they're both negative. So the cosine of that angle is going to be negative rad 2 over 2. And that's going to now multiply with the cosine of pi 6. Well, pi 6, if I were to reference that on the unit circle, that's really the first one in the first quadrant. And if I think about what the x value should be, the x value should be a larger value since it's further horizontally, or it's further to the right than it is up. So that's going to be the rad 3 over 2 value. Then it's going to be minus sine of 5 pi fourths. Well, that also, as mentioned just a second ago, should be the negative rad 2 over 2 because it's third quadrant. It's got to be negative for sure. And the two x and y values are both rad 2 over 2. And then the sine of pi 6, it's the same angle as before, but this time it's now the y value. Well, the y value was the smaller of the two because it's not very high above the x-axis in comparison to its horizontal. And so 1/2 would be its value. At this point, now I just go ahead and hopefully do what we know we can do with fractions, which is multiply the tops together, multiply the bottoms together, and then hope that we get a common denominator, or can get a common denominator. As we see here, we've got 2 times 2 in both cases, so the denominator here is just going to be a 4. And then with radicals being involved, if I ever multiply a radical with another radical, anything that's outside would just stay outside, so negative 1 times 1 stays negative 1. And square root of 2 times square root of 3 I actually can, because they're both inside radicals, multiply together and turn into a 6 inside. So now it's negative square root of 6. Second part, it looks like I've got minus a negative, so that's going to switch to addition. And then rad 2 times 1 is going to stay a rad 2. So we could leave it like that, or we could maybe make that little negative sign a little bit in a safer spot, so call it maybe rad 2 minus rad 6 all over 4. But honestly, it doesn't really matter between those two. If this is where you finished first and you just want to leave it there, there's really nothing I can do that combines radicals if there's addition or subtraction between them. It's only multiplication that I can really maybe change the values inside. So that's really as good as it gets unless I could rationalize. But if you think about the options that I'll be multiplying together, the sine and cosine ratios really are only a 1, a square root of 2, or a square root of 3 over 2 as like the ratios that we have on the unit circle. So really it's just going to be a bunch of rad 2s and rad 6s that I might potentially get as my ratios, at least for sine and cosine functions. So again, either of these two would be acceptable answers. I think the second version technically is a little safer just because the minus isn't accidentally maybe going to get moved all the way in front, right? If I put them negative in front of the fraction as opposed to only on the radical, that gives me a completely different value. So I personally like making, if I can, any negatives or a subtraction in the middle. That way, again, I just don't accidentally move it too far out front and create a different number than I really wanted it to be. But again, either of those would be acceptable. I don't want these coming back in decimal form, because after all, if I just wanted the value in decimal form, we would just type it into the calculator. But that also, kind of thinking of it, is a good way that you can check whether your answer is correct, is figure out what the decimal is of the result you just got and compare it with the decimal of what it would be originally. We just have to, again, anytime we type in sine or cosine or tangent, or any trig for that matter, just be aware of what type of angle we have, whether it's radians or degrees. This one specifically is in radians, so the mode of my calculator would need to be radians in order for me to accurately be able to check my answer, at least if I wanted to just type in the original part. All right, moving on to another example here. We've got this one and a couple more after that hopefully by the end of it will make it make sense on how we use the formulas that are presented. This one, again, it's now an angle that if it was on the unit circle, I would just reference whatever the tangent is on the outside that we've labeled. 15 degrees, unfortunately, though, is not one of those angles, so what we would immediately do at the beginning is just try and pick a couple of angles that do happen to have either sum or difference of 15. In this case, I would go ahead and maybe choose the 45, take away 30 degrees as my two options. And now I've identified the A and B values that I'm apparently going to use inside the formula. So formula-wise, the tangent difference formula is actually take the tangent of the A value, subtract the tangent of the B value, and then put it over 1 plus the tangent of A times the tangent of B. Again, that would just be something that would be on our reference page, so it's more just making sure that I know where the formula is, not so much having it quote-unquote memorized. But again, the more comfortable you are with it, the easier it will be to use, or maybe the faster we would be able to use it when it comes down to it. So if that's my formula and I've just identified a pair of A and B's that can subtract to equal the original angle, 15, again, I could have used like 60 minus 45 if I wanted to. But really from here, I just go ahead and substitute those values where I see the A and B, and then I'm going to replace with their values from the unit circle, hence why I chose them from the unit circle. And then I'll go ahead and simplify the fraction or whatever. Since this is one big fraction, I'll see if there's something I can do that makes it look a little bit more simple. So if I plug in those two values, on top I get tangent of 45, take away tangent of 30. On the bottom I end up with 1 plus tangent of 45 times tangent of 30. Again, if you wanted to use parentheses around it, you can, but with trig, it's just implied whatever is directly after it would be what's inside if it's an angle. So for this one now, if I reference each of the parts, tangent of 45 is actually kind of a nice number. Tangent of 45 is 1, minus tangent of 30, a little less nice. That one's the square root of 3 over 3. And then on the bottom, I end up with 1 plus those two same numbers multiplied together, so it would be 1 times square root of 3 over 3, which really is just going to be square root of 3 over 3. So it's like I can really just drop that 1, even though technically it existed there, and I really don't need that extra parenthesis either. So on the bottom, I've got 1 plus rad 3 over 3. On the bottom, or on the top, I've got 1 minus rad 3 over 3. And now it's just a matter of like, how do I maybe rationalize this? Because there aren't any variables on the bottom, so I do need to find a way to get that radical that's on that rad 3 over 3 that's on the bottom to somehow go away. The other issue I notice is there's fractions inside of a big fraction, so I'm actually just going to go after those immediately and just multiply through a 3 on top and on bottom. That way the fraction that's like the smaller fractions that are inside this big fraction will kind of take care of themselves. So that actually will now turn into 3 times 1 is 3, minus the 2 3's here would cancel, but leave the rad 3 on top. And then the other part, 3 times 1 again is 3. 3 times that fraction turns into just a rad 3 just like it did, but this time it has the plus in between instead. Now, this has been a while since we've had to worry about dealing with it, but if I ever have two terms and I need to rationalize, the process that we have to utilize, this was all the way back in like chapter 1, I believe, maybe even chapter 2, but what I would need to do is multiply by the conjugate of whichever part I'm trying to rationalize. So in this case, I'm trying to get the radical off the bottom, so I multiply top and bottom by the conjugate, which just happens to be the same two terms, but this time with subtraction, and then I distribute out. Well, the shortcut for conjugates is basically I just take the two things that I have. In this case, it's a 3, and then the other one is the square root of 3. I'll square both of them. So 3 squared gives me 9, square root of 3 squared gives me 3, and because it would have been a positive rad 3 and a negative rad 3, that technically keeps subtraction in between the two values. But notice that actually is going to turn into something pretty nice. It's just going to be a 6. On top On the other hand, I would actually need to think of this more like a FOIL type situation, or a Punnett square would also help, where I could do 3 times 3 to get 9. I get 3 times a negative rad 3 for a negative 3 rad 3. And then I could do the same thing here with the negative rad 3, distributing it through, so that gives me a second negative 3 rad 3, and then a negative rad 3 times another negative rad 3. Two negatives make a positive, and square root of 3 times square root of 3 is actually positive 3. So hopefully we notice here we've got a couple that are like terms. 9 and 3, they're both positive, added together give me a 12. And then a negative 3 rad 3 with another negative 3 rad 3 would give me a total of negative 6 rad 3s. And I've kind of pushed myself into a corner here, but technically I think we hopefully can see that the 12, the 6, and the 6 are all divisible by the same number. I could divide them all by a 6, and my final answer here would be 12 divided by 6 is 2, minus 6 divided by 6 turns into 1, but then still has the times square root of 3. So final answer would be 2 minus the square root of 3, or rad 3 if we want to say it that way, as the actual value. So tangent of 15 degrees, the original problem, has this ratio of 2 minus rad 3 as its value. And again, you could double check with a calculator. Here this time though, my angle is in degrees, so the mode of my calculator would need to be degrees. Type in tangent of 15, see the decimal, type in 2 minus the square root of 3, compare, and in this case they should be identical, which in fact they are. So we are good to go and move on to the next question. Now with this example, this is more one that would show, like, what if I don't actually have an angle provided, or what if I don't have any sort of referencing to the unit circle that I can do? Ultimately what we would then kind of think about doing is just utilizing what we hopefully remember about SOHCAHTOA, where if I give you two different ratios like this, where notice the angle is definitely different. One of them is angle A, the other one is angle B, and it does specifically say what quadrant the angles are in. That ultimately just helps me with any negative signs as needed. What I would immediately do with this bit of info is take the first one and just think, let's just draw a right triangle for it. It doesn't have to be perfectly accurate, but at least label like that's going to be my angle A, and it is sines ratio, so that would be the opposite side in my hypotenuse, which then I should be able to solve for my adjacent. Now if I do a very similar step with the second one, I'll just draw another triangle. This time though it's the angle B, and this time the opposite in this case is 1. My hypotenuse also is 3, and now I would just do the same thing, use Pythagorean theorem to figure out the last side. So if I go ahead and do Pythagorean theorem with each of these, square both numbers and then subtract. So the first one would become 9 take away 4, which is 5, and then take the square root of that, so it's got square root of 5. The other one is 9 with a 1, so 9 take away 1, it would be 8. Square root of 8 actually can be not rationalized, but simplified. 8's the same as 4 times 2. Square root of 4 is 2, and then it leaves the square root of 2 inside, so I would actually more think of it as the square root of 2 2 times the square root of 2 when it comes to actually setting up my ratios in a simplified form. Now I personally, for organization's sake, like to, because I know what sine of A plus B will require, in fact let's go ahead and just get that written on the screen. Sine of A plus B turns into sine of A, like this whole formula here is going to turn into sine of A times cosine of B, added with sine of B times cosine of A. Or sometimes the second one's written as cosine of A, then times sine of B. It's more just a matter of, do we want to keep sine first, or do we want to make the angle A be first? The order doesn't really matter. Just notice one time I do sine of A, the other time I do sine of B when I do the two terms. So again, for organization's sake, I like to personally just take the two triangles I have immediately and just write down what their values are. So down on the bottom right here, if we went with what's sine of A, well, they gave me that, but just again, I could look at the triangle. The opposite was 2, the hypotenuse was 3, so it's 2/3. So cosine of A, if we look at that one, that would just be the adjacent over the hypotenuse, so that's the square root of 5 over 3. And if I do the same thing with the B triangle, sine of B, technically they gave me, but again, it's the opposite over the hypotenuse, so that would be 1/3. And then cosine of B, it would be the adjacent over the hypotenuse, so 2 square root 2 all over 3. And now ultimately what I would do is just go back to our formula and just replace each of these 4 parts with the ratio I just identified. So as we just saw, sine of A will get to be replaced, and notice I'm not keeping sine, it's actually the whole grouping sine of A, that whole thing is just going to turn into the ratio 2/3. So notice there's no trig once I do the substitution. I'm replacing the trig with its corresponding ratio. Common mistake is actually putting like 2/3 where A is, but then keeping or accidentally writing down sine in front, and then at that point you kind of get stuck because technically you've broken some rules, which makes your brain probably kind of go, wait, what do I do now? So again, keep in mind this whole thing will always turn into just a single number, and then in the next line we really shouldn't see any words like sine, cosine, tangent, secant, like none of the trig functions should exist once I do the substitution. Anywho, if I go ahead and continue, cosine of b is the next part. So cosine of b we found to be 2 square root 2 over 3. If I could write a 2, there we go, over 3. And then it's added with sine of b. Well, we just identified sine of b not too long ago. That one was 1/3. So again, I've replaced the sine of b there. Last one here is the cosine of a. Cosine of a we identified was rad 5 over 3. And again, I didn't necessarily have to do all this stuff in the bottom right. I could have just each time referenced the correct triangle. I just like to, again, for organization's sake, as I mentioned, just at least have them all near each other so it's a little bit easier to identify, especially if this was like a, hey, part A, part B, part C type thing. One time I want to do sine, the next time I want to do cosine, and so on and so forth, and I have to switch from formula to formula. It might be beneficial to just have a nice, simple, easy place for you to look to identify it. But anyway, if I go ahead and continue the rest of the way, now I'm just going to multiply it out. I do notice that I've got 3 times 3 in both cases, so I could make this one single fraction, which is going to be over a 9. And then the first one, it looks like 2 times 2 times square root of 2. Well, that's really just going to be a 4 square root 2. And then the second one, I've got a 1 times the square root of 5. Well, that's just a square root of 5. And at this point, I would look to see if there was anything I could maybe simplify. I notice that I don't have any radicals on the bottom, so I don't have to rationalize. And actually, this is as good as I can make that. So that would be my ratio for whatever the a plus b angle would be. Now, the checking your work with this one is a little bit trickier to do, but what we could do is actually take each of these, solve for a, keeping in mind that it was 2 angles in the first quadrant, so I do need to make sure that if I solve for them, I could do it in radian form or degree form. It might be easier to do in degrees and just know that the answer has to fall between 0 and 90 degrees, even though it said 0 to 2 pi, or sorry, not 2 pi, but pi halves. But ultimately solve for the a, solve for the b, then actually add them together, figure out what that value would be, and then it would be now type in sine of whatever that angle is, see what that decimal is, compare it with the decimal of your fraction, and if you've done things correctly, they should match. But again, the checking with this is a lot more intense, a little bit tougher to do, and in fact it's almost tougher to do the math on the calculator compared to the actual doing the math here utilizing the formula. So if you want some help with that, by all means you can come talk with me. I can walk you through that process, but for the sake of making this video at least not an hour and a half long, I'll save the time and energy of that to just more of a one-on-one. If you wanted to see how to check it on a calculator, please just come find me. Now on to our last example. This one's just another one that's similar to what we just did, but this time now introducing what if the angles are maybe not so nice, meaning maybe what if they were in different quadrants, meaning negatives get involved. Process-wise isn't going to be much different. I'm just going to take the bits of info that they've provided, which it looks like they've given me a couple of different cosine ratios. They don't have to match. In fact, I could have given you cosine of A and then had the other one be like tangent of B. It doesn't really matter. I just needed to have at least one of the ratios for each angle, and then each one of those I just draw a separate triangle for. And again, just make sure I'm labeling things accurately. This one will be my A triangle, and this one over here I'll draw as my B triangle. Notice I'm essentially just kind of drawing them the same size. I'm not really worried about scaling. I just really want to make sure that I have the numbers in the right spots, and then I'll worry about the quadrants. Notice it does give me, hey, this first one, letter A, is in the 3rd quadrant, whereas the letter B is in the 2nd quadrant. So if we think back to like how does that affect some of the things that we might need to worry about, We could think of it as, if I'm going into each quadrant, what's my horizontal need to be, what's my vertical need to be, do I need a positive, do I need a negative, that sort of thing, and label appropriately. The diagonal, or the hypotenuse, remember, is always going to be a positive value, because I really don't have on the coordinate plane like a negative direction diagonally. We can make guesses, but there isn't anything that's physically defined. But we do have like a positive side horizontally or a negative side horizontally, meaning like using the x-axis or the y-axis to be able to do that. So again, here it looks like cosine of A is the -4/5, so I know that the 5, the hypotenuse, is supposed to be positive. And if I'm in the third quadrant, hopefully it makes sense that my horizontal must be a negative value, and then technically my vertical also will be a negative, even though I didn't draw it going down. I just know that it will have a negative value because of the quadrant it's in. And if I did Pythagorean theorem, it would be square each of those and subtract and then take the square root. Or you might recognize that this is just a 3, 4, 5 triangle, so that vertical side must be a -3. For cosine of B, similarly, it's going to be the hypotenuse is 5, it's positive. I do have a -2, that's going to be my negative horizontal. And since I'm in the second quadrant, that actually means because I would go up to get there, my vertical edge is going to have a positive value, so I don't need to introduce a negative sign there at all. And again, I would do Pythagorean theorem, square the two numbers and subtract. This time it's not such a nice, perfect Pythagorean triple, so it would actually be 5 squared is 25, take away 2 squared, which is 4, so 25 take away 4 would be 21, and then take the square root, so that's actually going to be square root of 21 for that last edge. Again, why is it positive? Again, that's having to do with, it's in the second quadrant, so my vertical side or vertical edge of that in relation to the angle should be a positive value. So now we'll go ahead and think about what do I maybe need for my formula. So for this one, if I go ahead and maybe off to the side just figure out or list out what are the things I might need to know. Might need to know sine of A, which it looks like that's not too tough to do. That's just -3/5 from SOHCAHTOA. Cosine of A they already gave to me, but cosine in this case would be -4/5. And then if I needed it, I don't technically need it for this one, but just to kind of show like how technically I can do all 3 original ones, and then if I needed the other ones, I would flip it, but all the formulas only use these 3. My tangent in this case would be -3 over a -4 for a positive 3/4. Similarly, I can do the same general thing with the sine of B. This time it's going to be the rad 21/5 for sine of B. Cosine of B would be the one that they gave me, but -2/5. And if I needed it, not that I do for this problem, but just to show that we can get it, tangent of B would be the opposite, square root of 21 over the adjacent -2. But anyway, if we go back to our formula, the question at hand wanted us to figure out what cosine of A minus B is. So that formula-wise is what's cosine, sorry about that, cosine of A times cosine of B, added with what's sine of A times sine of B. Maybe if you use these enough times, you kind of recognize sine, whatever the operation is inside, will keep the operation. So the sine formulas, if it's addition inside, it keeps addition with the formula. Cosine is kind of peculiar that whatever the operation is that we're doing, so in this case it's subtraction inside, the formula itself actually becomes its opposite operation. So subtraction or difference formula uses a plus in between the two parts, whereas addition uses minus. I don't know if that matters to you. Again, you'll have the reference page anyway, so it's more just identifying which formula am I using, writing it down, and then at this point now we're going to collect it together and just go, well, what do I know cosine of A is, and replace it with its value. So cosine of A we just identified to be -4/5. So I'm going to substitute it in place of it. Again, notice I'm not writing cosine, I'm just putting the ratio in its spot. Cosine of B, on the other hand, is going to be the -2/5. Added with the sine of A, I identified as -3/5. And then sine of B, I identified earlier as square root of 21/5. Now it looks like I have 5 times 5 as a common denominator with both of these, so that's kind of nice. That's going to just turn into 25 on the bottom. And now let's just figure out what each of the parts in the numerators would be. So -4 on top times a -2, that would be a +8 from the first product. I've got my plus sign, and then it's going to be -3 times the square root of 21, which is really just something I'd squish together. -3 rad 21. And honestly, doing plus a negative, that seems kind of silly. I would go ahead and just rewrite that using subtraction and maybe clean it up a little bit if I could, but this one I can't really do much combining since one of them has a radical, the other one doesn't in the numerator. I just have to keep them separate, and that would be my cosine ratio for that angle. So whatever a minus b would have been, whatever its value could be, this would be even tougher than the last example to check, because I'd need to utilize inverse trig functions, figure out what the ratio is, but then also make sure that I match an angle in the the correct or corresponding quadrant. And then I would subtract the two results, and then I'd have to figure out what the cosine. Like, there's a lot that goes into trying to check. But like I said, as mentioned, if you wanted to see or know how to do it, I'm more than happy to show you. It's just a matter of taking up time in this video. Doesn't seem the most useful. But anyway, I hope these examples have helped at least solidify like how the formulas kind of work. They all, in general, it doesn't really matter if it's addition or subtraction, or in other words, a sum or a difference formula. The process itself is still pretty similar, at least with the sines and cosines. Notice we use a lot of the sine and cosine ratios from the unit circle or from these triangles. Technically, we could do a tangent or a sum and difference for the tangent utilizing the same approach, where I just draw maybe a couple of triangles if it's maybe some ratios that were given instead of a specific angle. But again, those are like the two main ways that we're going to present problems. Either it's here's a value, use the unit circle to come up with it, or here's just a couple of ratios. Let's draw some triangles, label our sides, figure out all the ratios I might need, and then substitute them in place of all of the parts that we had. I don't know why I didn't put parentheses around those as I was substituting, but hopefully that makes sense. Like each time as you go, you can maybe just like check off, like I've replaced that, and so on and so forth. Again, you come up with what kind of works for you as far as a process, and just kind of pay attention to patterns and see if there's something that maybe you can consider a quote-unquote shortcut for yourself. Anyway, appreciate you taking the time watching the video. As always, if you have questions, come seek me out. I'll see what we can do. We can hopefully figure it out, work through a few more examples if need be. But as always, again, thanks for watching, and we'll catch you next time.